Okay, so I think now the recording is on. So we'll start with this Lagrange's theorem and just review what we did last time, and then I think after this we shall I'll talk about normal subgroups. So yeah, I think this is a good place to start. So we already stated this theorem last time, and what came before that was a proof. So today I will not go back to the proof. We'll just talk about the theorem and the consequences of the theorem. So this one says let G be a finite group and let H be a subgroup of G. So not very clearly it says a finite group. So this is only useful for finite groups. Then the order of H must divide the order of G. So what this simply says is that if a group has 10 elements, for instance, it cannot have a subgroup with 3 elements because 3 does not divide 10. The order of a group must divide, the order of a subgroup must divide the order of a group, so that the number of elements in a subgroup should be a factor of the number of elements in the group. I think there are people trying to join. Let's admit them. Okay, I think they are in now. We can proceed. So I hope you have gotten the content there. It says if you have a finite group, then the number of elements in any of its subgroups must be a factor of the number of elements in the group itself. And I've given the example, if you have a group with 10 elements, it cannot have a subgroup with 3 elements because 3 does not divide 10. Similarly, it cannot have a subgroup with 9 elements, it cannot have a subgroup with 7 elements, and so on. So if it has subgroups, then those subgroups will be either of order 1, 2, 5, or the whole group, 10 itself, which are factors of 10. So are there any questions on that?
No.
No questions. Good. So we will proceed. Now, the converse of this theorem is not necessarily true. So if we have a factor of G, the number of elements in a group, then it's possible that G may not have a subgroup with that number of elements. So for instance, it's possible to have, suppose you have a group with 12 elements. It's not guaranteed that you must have a subgroup with 6 elements. It's possible to have a group with 12 elements, which does not have a subgroup with 6 elements. We shall see examples of that later when we cover the symmetric group. So just being a factor is not sufficient, but it's necessary. It's necessary for a subgroup, the number of elements in a subgroup of a finite group, to divide the order of the group. That is necessary, but it is not sufficient. It does not guarantee that there is a subgroup of that order. But there is a case where that is guaranteed. The converse, if G is a cyclic group, finite cyclic group, then if D divides, if some integer D divides the number of elements in the group G, then the group will have exactly one subgroup of order D. So this is true for cyclic groups. I hope that is clear. So now we look at some consequences of Lagrange's theorem. So this example here says if G is a finite group, well, the corollary says if G is a finite group, then the order of A divides the order of G for any element in G. So A is an element in G. The order of that element in G, I think I need to rewrite this so that it's complete. So A is an element in G, and the order of A must divide the order of G. So we can try to prove this. So we earlier on saw that the order of A, an element A in G, is the same as the number of elements in the cyclic subgroup generated by that element. So remember, we denoted the cyclic subgroup generated by A by using these square brackets around A. So this notation simply means this is a cyclic subgroup generated by A. And the number of elements in the cyclic subgroup generated by A will be equal to the order of A. We saw this earlier. Now, if you apply Lagrange's theorem, since this is a subgroup, the number of elements in the subgroup must divide the number of elements in the group. And since these two are equal, it means the order of A must also divide the order of G, for the number of elements in G. Are we together? Yeah. Good. So here is one more consequence of Lagrange's theorem, normally better known as Fermat's little theorem. So if G is a finite group and A is an element of G, then A raised to the order of G will be equal to the identity. Remember, we have been denoting the identity of the group using this letter E. So E here refers to the identity elements in the group G. So for instance, if a group has 10 elements, then if you pick any element in the group, A raised to 10 will always be equal to the identity in that group, and not just for 10, any other finite group. So let's see if we can prove this. So first of all, we let the order of A be equal to M. And then by definition, if the order of A is equal to M, it means A raised to M should be equal to the identity element. Now, we have seen earlier that the order of A must divide the number of elements in the group. So it means M must divide the number of elements in G. So it means G, since M is a factor of the number of elements in G, then we can write this number of elements in G as a multiple of M. So we can write it as MK, where K is another integer. And if the order of G is equal to MK, we can write A raised to the order of G as A raised to MK. And we can split this, separate this. We have M on the inside and K outside the bracket as exponents. But we know very well that A raised to M is the identity because the order of A is equal to M. That gives us E raised to K, which is also equal to the identity. So that confirms that A raised to the order of G will always be equal to the identity. As long as G is a finite group, this will always be true. I hope that is clear. Are there any questions? So here, if you still need to look at that, you can look at it briefly as we, let me admit some people. I don't see anyone pending. Okay, so let's proceed. So we have looked at the two consequences of Lagrange's theorem. And also based on that, you can prove these two statements, that all groups of prime order are cyclic groups. So for instance, any group with 7 elements or 11 elements or 19 elements will always be cyclic. Second one says prove that all groups of order 5 or less are cyclic groups also. So again, that's the same. All groups with 5 elements or less are cyclic. You can prove this in your own time. I can give you 2 minutes to, or 1 minute to write down and attempt to prove, then we proceed. So try to do this and argue it out in your own book and see if you can figure out the two statements. So maybe I'll give you 1 minute to try. Then you can continue in your own time later. Is that okay? Can you hear me?
Yes. We are done.
Yes, solve these problems for me. Memaliza?
Ndio.
Okay. Have you found the answer? Can someone briefly tell us why number 1 is true? I thought you said Memaliza. Ilikuwa story too.
Panatufanya kuandika ndo tupitie jioni.
Okay, so try to solve this so that we can look at your answers later. Now, a lot of this material you can easily find online, so you can search for these things and prove. And, make use of all the resources you have. So now we move to a new topic. We cover the normal subgroups. So we will start with the definition. If G is a group and H is a subgroup of G, then H is said to be a normal subgroup of G if XH, X inverse is a subset of H. So if this set is a subset of H, and that should be true for any X that you pick from G. So if H is a normal subgroup of G, we usually will denote it by this. We have this H, then there's this triangle that is pointing to the left. It means H is normal in G. So there is no opposite for normal, so we don't have abnormal subgroups. So we only have normal, or if it's not normal, we say it's not normal. We don't say abnormal. So we only have normal. We don't have abnormal subgroups. I hope you have understood this. We shall do some examples to illustrate this, what this means. So this set here simply means you pick every element in H, multiply it by X on the left, and multiply by X inverse on the right. So every element in H here will be multiplied by X on the left and X inverse on the right. That's how you construct this set. Okay, so here are some examples of normal subgroups. If G is a group, then this group containing just the identity elements and the whole group are normal subgroups.
Excuse me, sir.
Yes.
Let me see the previous screen, please. I finish up cooking something.
You are still cooking something.
Thank you. I'm done.
Okay. So here are some examples of normal subgroups. These are two really basic examples of normal subgroups. That is E, the identity, is a normal subgroup, and then the whole group was also a normal subgroup. Those are the trivial examples. The other one that's a bit obvious is if G is an abelian group, then every subgroup of G will also be a normal subgroup. I think you can prove this part. Take this as an exercise, this second part. So this number 2, I have not done the proof, but all abelian groups will, for an abelian group, all the subgroups will be normal subgroups. Any questions on this? So any group that is commutative, a subgroup will be automatically, any of its subgroups will be automatically normal subgroups. Okay, we proceed. So let's look at another example. So we look at our favorite group, the dihedral group of degree 3, or what we call the symmetries of an equilateral triangle. So this is how we set them up. We had E, A squared, B, AB, and A squared B. We also had constructed some subgroups earlier, which we shall use. We call the first one K, consists of these two elements, E and B, and the second one is H, consisting of these three elements, E, A, and A squared. So we have two subgroups. We want to check if they are normal subgroups. So to check if they are normal subgroups, we need to go back. Let's go back to the definition. We need to do this. We need to check if for all X in the group, XH, X inverse will be a subset of H. So now, if you look at this definition, it requires this statement to be true for all X in G. So if it fails for just one element, then H also fails to be a normal subgroup. So when you are checking whether a subgroup is normal or not, if you can show that it fails for just one of the elements in the group, if this statement fails for one of the elements in the group, then that subgroup will not be normal. You don't need to check the others if you can find one for which it fails. So because we need to multiply by an element on the left and the inverse of the element on the right, we need to find the inverses of each of the elements, and we have listed them here. We had seen this earlier, so this is we just need to recall that A inverse is the same as A squared, B inverse is its own inverse. AB inverse is also its own inverse, and the same is true for A squared B. And the inverse of A squared will be A. Right? So we have all that information. So let's start with K. We want to check if K is normal. So we multiply by A on the left and A inverse on the right. We know A inverse is A squared, so I can replace it with A squared in the next part, the next point rather. So what this means is I need to multiply all the elements in K by A on the left and A squared on the right. So I do that for E, and I do that for B as well. And this is what we end up with. And it simplifies to this. You have E and A squared B. No, something is not right. Is that correct? Yeah, I think this is correct. We have E and A squared B. So you can see the problem here?
That is correct.
Yeah, it's correct. So, but now E squared is not a subset of K, because we have an element in this set that is not in K. So this A inverse is not a subset of K. And for that reason, this requirement fails for A, and we cannot, that means K is not a normal subgroup. So this requirement fails for A. Now you don't need to check for the other elements in D3 because you've already found one for which it fails. For it to work, it must work for all of them. If it fails for even just one, then K will not be a normal subgroup. So that's the conclusion we come to, that K is not a normal subgroup. So let's continue with the second subgroup. So this is the second subgroup, which is E, A, and A squared. So we work this out, BH, B inverse. And after the computations, we end up with E, A squared, and A, which is basically the same as H, and therefore is contained in H. So you can check all the others. So we try it for AB, and it turns out to work also. You have AB on the left, and AB inverse is just equal to AB. So when you're working this out, you just replace AB inverse with AB. The inverse of AB is itself. So when you work it out, you should end up with the same set again. So this set is contained in H. The same is true for A squared B. You end up with a set that is contained in H. And also the same is true for A. You have AH. This is obvious because A and A squared are already in H. Someone's microphone is on. Appearing with a.
I have a question.
Yes.
The first one, BH, B inverse. The first one, B, E, B, is it supposed to be B inverse, which is E?
B inverse is, B is its own inverse. So the inverse of B is equal to B. Let's go back to the previous slide. Okay. We wrote down all the inverses. Here.
Oh, I got it.
A inverse is A squared, B inverse is its own inverse. The same with AB, AB is its own inverse, and A squared B is its own inverse. So you need to use that anytime you're working it out. So we see here that after we go through all the elements in D3, this is true. If you pick any element G in D3, GH, G inverse will always be a subset of H. And therefore H is a normal subgroup of D3. So here we are lucky because this is a small group, so you can check manually. This is not always possible, and we shall encounter other examples later where you can't check manually, and you'll have to employ other techniques to check that a subgroup is normal. So here is another exercise for you. This time you consider the D4, the dihedral group of degree 4, or the symmetries of a square. And then there are two subgroups. We have E, A squared, so it's a subgroup with 4 elements. And then the other one is K is equal to EB. So using the same ideas, you need to determine whether these two are normal subgroups of D4. Are we together? So
Yes.
that's an exercise for you. There are more exercises in the typed notes that I shared under the topic for normal subgroups. So you should also find time to solve those questions. So we can move on to the next slide.
Just a minute, sir.
So try to, using the same ideas we have used in D3, you need to check if H and K are normal subgroups or not normal.
You can move on. Thank you.
So here is a theorem that shows us how to obtain more normal subgroups. If you have two normal subgroups, you can obtain another normal subgroup by getting the intersection of the two normal subgroups. So if H and K are two normal subgroups, then the intersection is also a normal subgroup rather. So we'll go through the proof. Earlier on, we'd already seen that the intersection of two subgroups is a subgroup. So the only thing here is, since we know that the two subgroups are normal, we just need to show that the intersection will also be normal using the information that the two subgroups are normal. So let's pick, for us to show that this H intersection K is normal, we need to prove this statement at the bottom here. We need to show that for any element you pick from the group, G multiplied by H intersection K multiplied by G inverse will be a subset of H intersection K. This is what we need to show. So we are going to go through the steps. So if you pick any element in the intersection, it means it must be an element of both H and K. That's what it means to be the intersection. And since H and K are normal, Gx, G inverse must be an element of H. And Gx, G inverse must also be an element of K. This is true because H and K are both normal subgroups. And for that reason, you can conclude that since Gx, G inverse is in both H and K, it must also be in the intersection for any element G in the group G. And therefore, I can, since X was from the intersection, if I replace X with the H intersection K, then now what I have here is a subset of H intersection K, because all of these elements are in H intersection K. It means this set will be a subset of H intersection K. But now this is precisely the definition of a subgroup being normal. So that means H intersection K is a normal subgroup. So a lot of these things require you to do a lot of repetition. So you don't just read this once. Make sure you keep reading. Are we together?
Yes.
So I can move on now.
Yes.
So let's look at
Wait a bit. Previous page.
so like I said, you need to do a lot of repetition for this. You keep going over and over until it sinks. Sometimes when you look at it in class, it looks quite clear, but it requires a bit of repetition for it to stick, or for you to fully understand it.
Can continue.
Okay. So The next is normal subgroups. So we are still on normal subgroups, but the next is a theorem. Let this phi be a map from G to H. Let it be a homomorphism, and G and H are just groups. So here we claim that the kernel of this map is a normal subgroup of G. So this is also a very useful theorem and comes in handy in many situations. So we'll prove it. Oh, what happened here in the slide? I think I made a, I'll fix it. If you pick X in G and K from the kernel, then we have the following situation. The image of XK X inverse, because this is a homomorphism, I can split this into like that. Because it's a homomorphism, this is possible. But I know that K is in the kernel, so it means K must be marked onto the identity in H. So E prime here simply means the identity element in H. And that means I can drop the identity and I'm left with just the image of X multiplied by the image of X inverse. But since this is a homomorphism, I can bring these two together, multiply them in the bracket. But I know this is the identity, which is also the image of, which is the image of identity is always the identity. We saw this earlier. So what have we shown? That this element, xk x inverse, is in the kernel. So any element you pick from the kernel, if you multiply it by x on the left and x inverse on the right, the element you obtain will still be in the kernel. And therefore we can conclude that x, so this is your set, the kernel. We already know it's a subgroup. I think we had shown that earlier. So at this point, we're just assuming it's a subgroup. So this subgroup is normal, the kernel. If you multiply it by x on the left and x inverse on the right, you end up with a subset of the kernel. And therefore, the conclusion is that the kernel of a homomorphism is a normal subgroup of G. So this is another way of finding normal subgroups. We've seen one way is if you already have two normal subgroups, you can obtain kernel. So you can obtain the intersection of the two subgroups and you will get another normal subgroup. If you have a homomorphism, you can find a normal subgroup of G by simply getting the kernel of the homomorphism, and you will have a normal subgroup of G. Any questions?
Does it mean that the phi of K is the identity element, the image of the identity element in the phi of xk phi
If
inverse?
the element is in the kernel, what happens to it when you map it using the, what is the image of that element under this map? If it's in the kernel, where is it sent?
Yes. E prime, the image of E, identity.
It's not the image of E, it's sent to E. Well, it turns out to be the image of E as well, but it's sent to E prime. So anything that is in the kernel is sent to E prime. E prime is the identity element in H. So that's why I'm able to replace this image of K here by the identity element in H. Does that answer your question?
Yes.
Okay. So this confirms that the kernel of a subgroup is a normal subgroup. So here is another theorem. Let's see, I think there may be some people trying to join. So another theorem. So this theorem says the following. if you have a homomorphism from G to H, where G and H are just groups, if H1 is a normal subgroup of H, so H1 is a normal subgroup of H, then the preimage of H1 will also be a normal subgroup of G. So that's another way. If I have a map between two groups, if I have a subgroup, a normal subgroup in H, then the preimage of that normal subgroup will be a normal subgroup in G. Okay. So the second says that if H2 is a normal subgroup of G, so here H2 is normal here in G. And if it turns out that the map is surjective, so this is important. Without this bit, this second part does not work. The map must be surjective. This homomorphism must be surjective. Remember, we gave it a name. A surjective homomorphism is called an epimorphism. So if H2 is a normal subgroup of G and phi rather is surjective, then the image of this subgroup will be a normal subgroup of H. So if you pick out all the elements in H2 and find their image in H, that image will be a normal subgroup in H. Are we together?
Yes.
Yes.
We are going to prove this shortly. So,
excuse me, sir. Excuse. Yes. Could you kindly go back to the last slide for a second?
The second is over.
Okay, yeah, thank you.
Okay. So you actually meant a second. Okay. If anyone else needs to write anything, I think I'll leave it on for a few more seconds then. So let's go next. Let's go back and so we want to prove this first one. This first one says is if H1 is a normal subgroup of H, then the preimage of H1 must be normal in G. So let's check this. So we want to show that the preimage of H1 is normal in G. So let's pick any element in the preimage and pick any other element A in G. Now, if X is in the preimage of H1, it means the image of X must be in H1 under this homomorphism. So we want to check what is the image of AX A inverse, where X is some element from the preimage of H1 and A is an arbitrary element from the group G. So using the fact that size is a homomorphism, we can split this into 3. But now we are aware that H1 is a normal subgroup, right? So if you pick any element from H multiplied by an element in H1 and multiplied by the inverse of the element you picked from H, you will always get an element in H1 because H1 is a normal subgroup. So remember, these are elements. The image of A is an element of H, and so is its inverse. And this is some element in H1. So this statement is true for all elements in H1, since H1 is a normal subgroup of H. So therefore, we can conclude that this, since this element is mapped onto some element in H1, then it must be in the preimage of H1, right? So if you pick any element A in G and any element X in the preimage of H1, then we have AX A inverse will be in the preimage of H1. And this means if you extend this replace X by its by the pre-image of H1, then I can conclude that this, if I multiply A by the pre-image of H1 and A inverse on the right, I will get a subset of the pre-image of H1. And that shows that the pre-image is a normal subgroup of G. So I think the one thing maybe that is missing here is that you need to show that the pre-image of a subgroup is a subgroup also. So this diagram tries to illustrate this. So I have the group G on this side. I forgot to label this. So G is a group on this side, and H is on that side. So you can try to study this diagram, and you will see that you'll see the explanation. So I'll give you a minute or so.
We cannot fully see the diagram.
So does it make sense? So this is a group G. This big circle here is a group G. On the other end, this black one is H. Then we have a subset of H, which we call H1. And all the elements here, which are mapped into H1 or onto H1, we label them phi inverse H1. So this is a pre-image of H1 in G. So the claim is that if H1 is normal in this group H, then this pre-image will be a normal subgroup in G. And that's what we have shown. Any questions? So we move to prove the second part. So I'll go back to the theorem so that we can be clear on what we are proving. So the second bit, we are claiming that if H2 is a normal subgroup in G, and the map is surjective, this homomorphism is surjective, then the image of this subgroup of G will also be a normal subgroup of H. So here's a proof. Now we already been given that H2 is a normal subgroup, and therefore for any element H I pick in H2 and any element I pick in G, this will be true. AH, A inverse, will be an element in H2. So we can now check. So if you want any element in the image of H2 will be of this, will be written as phi of H. And any other element, since the map is surjective, any element in H can be written as an image of an element in G. So let's pick A in G. Then this element multiplied by the image of H multiplied by the inverse of the image of A. Because this is a homomorphism, we can put all these back in the brackets. But you know that AH, A inverse is an element in H2. So it means since this is picked from H2, its image must be in the image of H2. Right? Now, since the map is surjective, if you pick any y in H, we can always find an element A in G such that phi of A is equal to y. So if you have y, phi H, y inverse, it will be phi A, phi H, and the inverse of phi A. And we have shown that this will always be an element. I mean, it will always be an element in the image of H2. And from there, we can conclude that y multiplied by the image of H2, y inverse will always be a subset of the image of H2 under this map, this homomorphism. So that is precisely the definition of a normal subgroup, and therefore we can conclude that the image of H2 is a normal subgroup. So the other thing that we have not proved in this part is that a subgroup, if you have a homomorphism, a subgroup will be mapped onto a subgroup. So the image of a subgroup is also a subgroup. That's the one thing we have not proved, but you can prove that in your own time. So it's really important that the map is surjective, so that this statement is true for all values y, all the values, all the elements in H. Any element you pick in H, this will be true. If the map is not surjective, then there are some elements that will be left out, and they will not be part of the. They will not. Then it will just be. It may not necessarily be a normal subgroup in H. It may be a normal subgroup contained inside another subgroup of H, but not H itself. So this part that says the map is surjective is really important for this to be a normal subgroup in H. So again, the diagram illustrates that we have a subgroup H2 in G. The subgroup is mapped, the image of a subgroup is in H, and the claim is that if H2 is normal in G, then the image as a subgroup of H will also be normal, a normal subgroup H. Any questions? No. Okay. So there are different ways to characterize a normal subgroup. So this theorem tries to put them all in one place. So we have already defined a normal subgroup. So we have the definition of a normal subgroup, and this is how we denote if a subgroup is normal in a group. So H here is a normal subgroup of G, and we have a definition of this before. But we are claiming that these four statements are equivalent. Equivalent simply means I can replace any one of these statements with another, any other in the list. So if I want to prove that a group is normal, subgroup is normal, I could just use the definition. That's the first one. I could also use, if I can prove this, then it also means a subgroup is normal. The third one also means that any left coset will be equal to the right coset. So this doesn't mean that the two cosets, that they are commutative. It just means this set has exactly the same elements as this set. It's not. It doesn't mean that the group is commutative, but it turns out that this set rather, will have exactly the same elements as this set, so that any left coset of X, any left coset of H rather, determined by X, will be equal to the right coset of H determined by X. So this also means that a subgroup is normal. And also, if a subgroup is normal, if I multiply any two left cosets, I should also get another left coset. So if I multiply the left coset determined by X by the left coset determined by Y, I still get another left coset of H determined by the product of XY. So if I want to prove that a subgroup is normal, any one of these conditions is enough. If I can use the definition, that is fine. but sometimes it's more convenient to use these other conditions. So if you want to prove this to be true, what we need to show is that 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. That way we shall have proved that these statements are equivalent. But the important thing is that if you want to prove that a subgroup is normal, you can use a definition. I think we have seen how to use a definition before, but these other statements also, any one of them can be used. If you use one, you don't need the other. That's why we say they are equivalent. So we're going to show that 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. If we show that, then we'll have proved that they're equivalent. So let's try the first one to show that 1 implies 2. So one tells you that H is a normal subgroup. So you suppose that H is a normal subgroup of G. Then by definition, this statement will be true. For any X I pick from G, XH, X inverse will be a subset of H. And also using the same definition, this X inverse H and the inverse of X inverse, which can be written as X inverse HX, will also be a subset of H. Again, this just follows from the definition of a normal subgroup. So I can write H as EHE, but E is the same as X inverse. And also I can have X inverse on the other end. And I can, since the operation in a group is always associative, I can put my brackets anywhere. So I choose to put them here. But I already know that this set is a subset of H. So I can replace it with H to make this set bigger. So I replace this with a bigger set so that this set now becomes a subset of XH, X inverse. Right? So this means that H is a subset of XH, X inverse. But by definition of a normal subgroup, XH, X inverse is a subset of H. So what does that mean? You have these two inclusions. It means that the two sets must be equal. So if you want to prove that two sets are equal, you must show that each of them is contained in the other. So here we have shown that from the definition, which was the assumption in one, that H is normal, we have this inclusion. XH, X inverse is contained in H. And then we have also shown that H here is contained in XH, X inverse. So that forces them to be equal. So we have shown that 1 implies 2. 2 claimed that XH, X inverse will be equal to H as long as H is a normal subgroup. And this should be true for all X in G. So the next part is to assume that 2 is true. So we can go back and see. The second statement here is this. We assume this is true and show that if this is true, then number 3 will be true. So if 2 is true, that means if XH, X inverse is equal to H, we can use it as follows. We need to show that the left coset is equal to the right coset. So we just set up the right coset determined by X, which is XH, but 2 tells us that H is equal to XH, X inverse. So I can replace H with XH, X inverse, and then X and X inverse will give me the identity. So identity, I can lose it and I'm left with just XH. So here we have shown that if 2 is true, that is if XH, X inverse is equal to H, then this right coset, HX, will be equal to this left coset, XH. So we have shown that the left coset determined by of H determined by X will be equal to the left coset of H determined, the right coset of H determined by X, if H is a normal subgroup. This should be X. not H, because the right coset is the right coset of H determined by X. So here we should have X, not H. Any questions? So we need to show that 3 implies 4. So if you check here, we need to assume that 3 is true and prove that if it is true, 4 must also be true. So to show that 3 implies 4, suppose 3 is true, that means hx is equal to xh for all x in G. Then we can do the following. We multiply 2 left cosets, and since since the operation is usually associative, you can put our brackets anywhere. And since this is true for all x in G, then I can write hy as yh. So I'm left with this as xy and hh. So this is just the same as xyh. So hh is equal to h. You can prove that. I've given you that assignment down here to prove that hh, if h is a subgroup, then h will just be equal to h. So what we have shown is that if you multiply any 2 left cosets, you still end up with another left coset if H is a normal subgroup. We have used the fact that H is a normal subgroup and assumed that statement number 3 was true. So now we have shown that 3 implies 4. So now we need to show that 4 implies 1, and then we shall have shown that these 4 statements are equivalent. So suppose xh is equal to xy for all xy in G. So we assume that 4 is true and show that it will imply that H is a normal subgroup. If that is the case, then xh x inverse can be written as xh x inverse, and you can multiply by the identity because the identity doesn't change anything. And then I can replace the identity with a bigger set, that is H, and that guarantees that this will now be a subset of this new bigger set, because this identity is already contained in H. If I replace it with a bigger set, then what I have here turns out to be a subset of this bigger set, xh x inverse H. Now we use the fact that xh yh is equal to xyh. This should be xyh, sorry. This is not complete. We are using this statement here, that xh yh is equal to xyh. So there should be a capital H here. So using this, it means xh, x inverse H is the same as x inverse H. But x inverse is just the identity. So I can replace it with the identity, which gives me H. But then what have I shown? I have shown that xh x inverse is a subset of H. Remember, we have a subset here for all x in G. So any x I pick from G, xh x inverse will be a subset of H. But what does that mean? It means H is a normal subgroup. So we have shown that 4 implies 1. So that proves that these 4 statements are equivalent, and any one of them can be used to prove that a subgroup is a normal subgroup. Any questions? So tuendelee. Can you hear me?
Yes.
Thank you. So you have any question? You note the corrections here. I'm going to fix the slides, then I'll share the corrected ones. This one is supposed to be X, Y, H here. Capital H in particular. So there's an exercise for you here. You prove that a subgroup of index 2 is a normal subgroup. So a subgroup of index 2 means a subgroup that has only two distinct left cosets. So if you have a subgroup which has only two distinct left cosets, the claim here is that that subgroup must be a normal subgroup. So this is another exercise for you to prove. So we'll just make some definitions and stop there for today. No, not really definitions, just one definition here. So we let G be a group and H be a subgroup of G. Then the set of all distinct left cosets of H in G, usually denoted by G / H. So you have a / and H. So remember, this is a /. It's not a vertical line. It does not. It's not a backslash. It's a /. So this is a set containing all the left cosets of H in G. So as an example, if we take D3 or the head-wall group of degree 3, which has these 6 elements, we pick H as this subgroup EA squared. We saw this was a cyclic subgroup generated by A. Then we also saw that the distinct left cosets of H in G are just 2. So there is this H itself. One of the left cosets will always be the subgroup, and then the other left coset was B, AB, and S squared B. We did this earlier and saw that these are the only two distinct cosets of this subgroup H in D3. So that means if you label this second coset as T, then the set of all distinct left cosets of H in D3 will simply be these two sets, H and T. So using this notation, we are now finding the set of all distinct left cosets of H in D3. So there are only two, and we put them here in the set. So you have some work here. You have this left coset, K is equal to EB. So you are supposed to work out the set of all distinct left cosets of K in D3. So we'll stop there for today. Tomorrow we'll start on some theorems. So as much as you'd like us to continue, we have to stop. So as much as you'd like us. And are there any questions?
Yes, I had a question. Let H be a subgroup of G and let A in G.
Right.
Then prove that AH is equals to H, if and only if A is in H.
Yes, you are supposed to prove that.
Yes, you are supposed to prove that.
No, it was a challenge. That's why I'm now asking.
You want to send the challenge back to me?
Send the challenge back.
Now,
To the class.
a lot of these you will find solution on the internet. So just simply do a quick search. You will find a lot of PDFs with these solutions. So, but you need to check that if A is an element of H, then any element in AH will be contained in H also. Right? That is because of closure. So this, if A is already an element in H, this left coset of H determined by A will always be a subset of H, because if you multiply anything in H by an element that's already in H, you can't get a new element. Remember, a subgroup is closed under the binary operation. So if I multiply anything in H by A, I can't get anything outside H. So I can always guarantee that AH is always contained in H. So in the same way, if I need to show that if I pick any element in H, it should also be a subset of AH, as long as A is an element of H. So here you will have to apply the cancellation laws. So AH must be equal to H because of the cancellation laws. In other words, if you multiply everything in H on the left by A, you will not get anything outside H, and the number of elements in AH will still be exactly the same as the number of elements in H. And therefore, the H must be contained in AH. So those two inclusions will tell you that that if A is contained in H, then AH is equal to H. And also now you can prove the converse. If AH is equal to H, then A must be an element H. So you can try that and put it in your own words. Let me know if you are not able to do it in the next class, then we can review it. But there are plenty of solutions on the internet for this. You just need to do a quick search. You will find so many. I can also write it out for you and share. So I think we'll stop the class there for today. So